Okay, let's come back to our class. So basically, in the last lecture, we have been talking about the discrete Fourier transform. I think alternative name is also known as the fast Fourier transform, FFT or DFT. So they are basically representing the typically the same thing. The idea is that we have been talking about how we want to do a fast matrix vector multiplication here, and basically the strategy that after we discuss this is that basically we want to utilize root of unity. So basically, the idea is that we want to consider such kind of axis, and basically we in general is basically like a problem like this. We have this omegas, and we want to correspondingly solve this problem. And now it comes to the part of making a divide and conquer here. Okay, so for the divide here, you can clearly see the strategy is that we are going to divide according to even and odd terms. So basically, we break the polynomial up into even and odd powers. Okay, so basically the A even here is basically A0, and basically we are just going to follow in this specific example. So basically we're going to follow this example. So here we're going to A even is going to be A0 plus A2 times x plus A4 times x squared plus etc. An over 2 minus 2 x to the x 2. Sorry. Oh, I think here I probably made a typo. N minus 2. Here, so basically we are assuming that n is a power of 2 here, so basically n over 2 here is an integer. And also on the other hand, a odd of x equals to a1, say 3x squared. So basically this is the way we are going to make the division of a even, a odd. And we know that ax and then equals to a even x squared plus x times a odd x squared. So maybe let me close the door. Okay, so after having the a even, a odd polynomials, we know that ax is going to equal to a even of x squared plus x times a odd of x squared. Okay, so this is the divide, and basically we know we need to understand the conquer part. So for the conquer part is that basically we recall that for divide and conquer, we can call the algorithm recursively. So that is basically saying that we have the evaluation of a even x and a odd x. At the n over 2th root of unity. So that is basically by our notation here. That's basically v0, v1 until v of n over 2 minus 1. So assume that we have the conquer here and we recursively call the algorithm and solve this. And finally, we can combine. So the way that we are going to make the combine is just that we directly look at into this formula. So basically for a of omega to the k, it's actually going to equal to a even of v to the k, because we are actually having that omega squared equals to v here, plus omega to the k. So this is basically for arbitrarily k between n 0 and n over 2 here. So on the other hand, we can also consider like this formula. So basically, this equals to a even v to the k minus omega to the k here. So here we basically utilize the fact that omega k plus omega to the k plus n goes to minus. And actually, speaking of the v part, so basically we know v to the k equals to omega to the k squared equals to this. So basically, after having all these calculations, so basically the algorithm, basically the discrete Fourier transform, it is relatively straightforward. So basically, I recall that we have all this kind of calculation about like how we are going to do the things recursively. So basically, we have this algorithm, discrete Fourier transform, or FFT, fast Fourier transform. Okay, so basically the FFT n a0, a1, an minus 1. So for the base case, base case where n equals to 1, we just return a0. And furthermore, else, so we just call this this FFT recursively. So assume that maybe, for instance, for the odd part, assume that we have the these values basically d0, 1, e of n over 2 minus 1. Assume these are the iterations from the odd part. So the odd part maybe is like a3, 1. And similarly, we can also recursively call the odd, even part. FFT n over 2, a0, a2, until n minus 2. So basically, those are our calls recursively. And actually, for k equals to 0, 2n over 2 minus 1. So after we call the FFT recursively, we need to recover the current function, the polynomial values. So basically, for doing that, we just have omega to the k equals to, we have a k here, divided by n. And also yk equals to ek plus, and also this. And after having all of this, we return on this value. Any questions here? So this is basically a formal writing of the algorithm, the fast Fourier transform that we are actually having here. The main idea is that still, as we just discussed, that we divide the polynomial into odd polynomials and even polynomials. And the point that we want to query for the function values are basically correspond, originally it is nth root of unity. And basically in the recursions is n over 2th root of unity. And basically we correspondingly call the FFT in the n over 2 case. And then we recover this corresponding function values by this formula, which is actually directly given by this. So any questions? So I think for the calculation of fast Fourier transform, I mean, maybe you are not that familiar with like calculation complex numbers. Maybe you need to think a little bit more further this. But I think hopefully the intuition is clear to you, and just feel free to ask if any questions. Sure. I will first finish FFT and then talk about inverse. Okay. So this is basically the FFT, and we can feel free to actually write down a theorem here. So a theorem that we have is that the FFT basically evaluates a degree n-1 polynomial at each of the nth root of unity in all n log n steps. I guess this is relatively straightforward. It's because just because the running time is basically Tn equals to 2 times T of n over 2. Because we have basically the even polynomials and odd polynomials. So we have like a 2 here. And basically also the problem size becomes n over 2 here. And also the further cause is On here. It's just like we need to recover all of this and also make the subsequent calculations. And this is basically suggesting that Tn is just On log n, as we claim. So that is to say, I think maybe let me actually recall that we draw this. To recall that we draw this. So this is basically saying that we have gotten an efficient algorithm from a coefficient representation to a point value representation. So basically for this direction, is O of n log n. And I think for the inverse of a fast Fourier transform is basically the other direction. And I'm going to introduce in a minute. So here I think before we do that, I think another thing that we want to take a look at about like how the coefficients are actually going to work. And I think actually we have this example where the degree of the polynomial equals to 7. So basically we have this A0, A1, A2, A3, A4, A5, 6, A7. So basically, in the division of odd and even polynomials, it is basically we divide them into like this is basically a group of even polynomials. We have A0, A2, A4, A6. And also the other group, on the other hand, it is going to be A1, A3, A5, A7. And after that, I mean, when we further make the recursive calls, I mean, we call actually the even odd polynomials in this group of coefficients. We actually got like A0, A4 for the even part, and now A2, A6 for the odd part. And here we actually have A1, A5 for the odd part, and actually I think I'm probably seeing the other way. Sorry, yeah, A1, A5, they are actually the odd part, and A3, A7, they are the odd part. Actually, we have A0, A4, 2, A6, A1, A3, A7. So here, I think what is a little bit interesting is that we consider the binary representations of these numbers. So here, the 0 is 0, 0, 0. 4 is 1, 0, 0. 1, 0, and 6 is 1, 1, 0. And 1 here is 0, 0, 1, and 5 is 1, 0, 1. And actually, 3 is 0, 1, 1, 7 is 1, 1, 1. So somehow we notice that, so basically the recursion, excuse me. So the recursion is basically called, somehow it's so-called like a bit reversed order. So what do I mean by that? So basically we know that this is the part of even, and this is odd. I think I got a little bit confused here. Sorry, this is even. I think I'm probably saying it wrong here. So this part is even, this is, I think I said it wrong here. But yeah, but this is part is even, the left part is even, the right part is odd here. And actually this is even, this is odd. So we see that basically this order of even, odd is basically in a reverse bit order. So basically you look at, for instance, like A0 and A4 here. So this is basically the part where actually at the bottom, I mean, we make the final recursion here, and this is part of final, it is still even, and then it's 0. But here it is odd. It is actually A4 here. But you see like the other 2 bits, they're actually even. So basically looking at the structure, where actually it is at, I mean, at this kind of recursion. So you can actually, I mean, maybe a practice algorithm is not really looking at this from like a top down, this kind of way. You can also look at this from like a bottom up. I mean, this kind of things. So basically, you have this bit representations of the coefficients. You can actually group them basically in this kind of a reverse bit order sense and actually scale them up basically in this kind of sense. But this is just an interesting thing that we want to make the observation here. Actually, something that is satisfied here for this bit reversed order when you call this kind of fast Fourier transform algorithm. Okay, so any questions about this? Okay, so the remaining question here is that basically we have been talking about this fast Fourier transform from coefficient representation to a point value representation. So of course, the remaining question is that we want to consider that the inverse version. That also we want to have like an efficient algorithm from point value representation to coefficient representation. Okay. So how about point value to coefficient? So here, I think maybe a good way to look at this is that we still look at this linear system. We look at this linear system. So that is basically saying that we need to have a it's a connection issue with my iPad. Oh, I guess it's working. Okay. Yeah, no idea what just happened. Okay, so I guess now here, if you want to talk about inverse fast Fourier transform, it is basically saying that we instead of having an input as a vector of the a's here, we basically have an input now all the y's, but we need to recover the coefficients. So basically something like this. So I think, I mean, from a linear algebraic perspective, a very natural way that you want to do this is that you just apply Fn inverse here. So I think here, I mean, because Fn is a fixed linear system, basically a matrix here. So basically this Fn inverse is basically a fixed value. So it suffices that if I write down a matrix here, and basically if it multiplies the Fn to be identity, I guess we are good. So let me just write down the correct form of the Fn here. Sorry, the Fn inverse here. So let's call it like a Gn. So claim Gn is good. Okay. Oh. So a claim that we are going to make here is that the inverse of the Fourier matrix is given by the following formula. So the Gn goes to 1 over n times this. So the coefficients now inside this matrix is going to get a little bit twisted. It's basically something like this. 1 in the first line. So 1, they're actually in the same column. So 1, omega to the minus 1, omega to the minus 2, omega to the minus and minus 1. 1, omega to the minus 2, to the minus 4, the minus 2 times the minus, etc. I guess let me actually zoom in a little bit because it's a little bit small here. And finally, this is omega to the minus n minus squared. It's basically this. So we basically need to prove, and if we want to prove that this is correct, we basically need to show that Fn, Gn, it is identity. So let's actually look at a specific entry of this Fn-Gn. So Fn-Gn use entry kk prime, actually equals to 1 over n, summation of j from 0 to n minus 1. And this equals to omega kj times omega minus j prime j. And this is actually going to give us 1 over n times the summation of j equals to 0 to n minus 1 omega k minus k prime j. So here we say that this equals to 1 if k equals to k prime and equals to 0 otherwise. So if we can prove this, I guess we just finished the proof, because basically if the entry at the kk prime equals to 1, if and only if k equals to k prime, the other place equals to 0. This just means that this matrix Fn-Gn is the identity matrix. Okay, so how do we establish this? So this is just due to the summation lemma. So what do I mean the summation lemma here? So it's basically the summation of j equals to 0 minus to the minus 1. Let's call it omega to the Lj equals to n if L or mod n is basically L is an integer multiple of n or 0 otherwise. So basically we are showing a thing like this. So is this clear so far? Because basically we are here actually combine the things together here. So if this summation lemma is correct, I mean, basically this k and k prime, I mean, both k and k prime, they are actually taken from n here. I mean, it is only possible, I mean, it is if it is a multiple, integer multiple of n, it is this can only happen if k equals to k prime. So, I mean, if the summation lemma is correct, I mean, if we know that on the right-hand side equals to, for instance, equals to 1, it must be the case that it's the integer multiple of n, and actually we make the conclusion that k equals to k prime. And otherwise, if it's equals to 0, I mean, it's just the other case that we can conclude from the summation lemma here. So let's prove this. So this is actually a very basic effect from complex numbers. But for the completeness, let's actually prove this here in the class. So if L mod n equals to 0, I guess this case, we know that L is a multiple of n, and this just suggests that omega to the L equals to 1, and this directly suggests that the summation is equals to 1. On the other hand, so each nth root of unity omega to the k is a root of this xn equals to 1. This is actually equivalent to 0 equals to x to the n minus 1. But this actually equals to x minus 1 times x. So if omega to the L not equal to 1, we must have so basically we know omega to the L to the n, I mean equals to 1 is basically a root of unity, nth root of unity. Then basically we know that 0 must equals to basically we know that 0 must equals to but replaces by omega, sorry. Replaces by omega to the L, and basically all this by omega to the L. So basically we know this must equals to 0, but this part, it is not equals to 0. So this just concludes that the conclusion is correct. A summation of A equals to summation must equals to 0. And this concludes everything. Okay, so is this clear to you that basically this Gn, this is the invariance of the matrix Fn? Okay, so this basically gives us the algorithm. So the consequence. I mean, basically, for such kind of transformation, I mean, for the Fn here, we have been describing the FFT here, so the fast Fourier transform. So basically, we can see that we make such kind of recursive calls, and basically we recover the corresponding evaluation values accordingly. So this matrix Gn, actually, you see that this form is actually not a big difference compared to the form for the FFT. This is just like due to the nice property of these roots of unity here. So we can make the conclusion to saying that to compute inverse FFT, apply the same algorithm. But use actually omega to the minus 1 equals to e to the minus 2 pi over n as the principal f of unity and divide by n. This divide by n just came from this. And actually the fact that actually if k equals to k prime, you're actually getting a summation. I mean, you get n identical terms, all of them, they are actually equals to 1. So you need this renormalization factor, this 1 over n here. So basically, you just literally, I mean, for the inverse FFT, you just run this algorithm. But here, it's just like for the omega here, you want to be careful. So instead of using this omega to be 2 to the e to the 2 pi over n, you replace this by e to the minus 2 pi over n, and you divide everything here by 1 over n here, and you get the inverse. Okay, so is this clear? Okay. So we just copy this. You just copy this. So basically, we also make a little bit calculation here. So we know that for inverse FFT, that is basically from point value representation to coefficient representation. For this part, we can also do this in a very decent cos O of n log n here. So having both directions, we get a very important direct theorem here. So multiplication of 2 degree n minus 1 polynomials x O n log n steps. I guess I should mention with I mean, typically with coefficient representation. As inputs and outputs. So basically, we want to multiply two degree n minus one polynomials. So we are given with their coefficient representation. And the output that we are supposed to give are also their coefficient representation. So I'm saying that using this observation based on FFT and inverse FFT, we can actually finish this calculation. I mean, instead of computing everything here in a brute force sense using cos n squared, we can actually finish this task in cos O n log n here. So how do we actually do this? I guess let me just draw a roadmap here. So the input is that we have A0, A1 until an minus 1, and we have B0, B1, with Bn. So those are coefficient representation. So the thing here that we can do is that we apply FFT. Basically, the cos is O of, maybe let me draw like this. FT. So here we have those coefficients. So maybe we can talk about what is the precision that we want. So here we consider the roots. I mean, basically we do it a little bit further. So we have ax0 until ax 2n minus 1. So basically we consider the 2nth roots of unity. So that is basically to make sure that we basically make sure at this part. Basically, we want to be careful with this sentence. So having like a point value representation, if you want to determine a polynomial, so we really need 2n minus 1 points to really pin down this function. This polynomial. So that is the reason why here, I mean, we require a little bit larger, n here that we can consider 2nth roots of unity here. But this is not so difficult. That in general, it's just like multiply n by 2 here, and actually the cos is still O n log n here. 2n minus 1 here. And then for this place, we just call it a point value multiplication. And this cost is On. And basically after having this, we got the corresponding function values, basically. Just like this, Cx0 until Cx2n minus 1. And basically for the last step, we just call inverse FFT. And this causes O n log n. We recover the C values. C0, C1 until C2n minus 2. And this is also actually the output is a coefficient presentation. Okay, is this clear to you? So we basically see that this fast Fourier transform is something that is very intuitive, that basically we have like a very good transition between coefficient representation and point value multiplication. So when we want to consider multiplication of two polynomials, so we know that a direct way is that the point value multiplication is so straightforward. So I mean, although the input and output as required are coefficient representation, we just correspondingly use the FFT and inverse FFT and transform to and from a point value multiplication, and basically we accomplish this task. Okay, so I guess here, I mean, actually, when we talk about the Karlsruhe algorithm and also the Strasson's algorithm, we have been talking about how this algorithm, work in practice. So here, let me also make a little bit further discussion here. So basically, FFT in practice. So FFT is indeed super helpful in practice. So this is actually, for instance, optimized in C library. And actually, there are a lot of good numerical package for FFT, and people have been really improving this. So basically, for instance, also like the sorting algorithm. I mean, sorting also takes cost and log n. And people, I mean, from an engineering perspective, people have been really working hard to improve the corresponding cost. And for instance, for this actually won the 1999 Wilkinson Prize for numerical softwares. And actually, I mean, we have been talking about, I mean, we assume that n is a power of 2 here. Maybe, for instance, if it's not a power of 2, we just like assume that some of the coefficients are 0. So this is definitely not a very efficient way. But in general, people have been really optimized this hard. So of course, I mean, asymptotically, we know that in general for n, the cost is O of n log n. But actually, there are good algorithm or n log n algorithm even for prime sizes. I mean, and actually, this is efficient in general. I mean, from engineering perspective. Okay, so basically, this finishes like the algorithm part of FFT, and maybe let's talk a little bit about the application of the FFT here. So, for instance, we have been talking about the Karlsruhe algorithm, basically integer multiplication. So, for integer multiplication, I guess the problem we can say that we have two n binary bit integers. A equals to a n minus 1, a1, a0. And actually on B equals to bn minus 1, b1, b0. Compute their product. So here, what do we actually what to do here? I mean, in general, I mean, we can actually think about, we want to actually regard this integer multiplication problem as like a polynomial multiplication problem. So in general, we can consider something called like a convolution. So basically, input new polynomials. Where ax equals to a0 plus a1x, an minus 1x2 plus 1, x also equals to this. So for the integer multiplication problem, we note that actually a equals to a2. Just specifically the function value at 2. And actually b also equals to b2 here. So we compute, I mean, from a polynomial perspective, because this is just like, on the other hand, this is like a coefficient representation, and this b0, b1, bn minus 1. This is also like a coefficient representation. So we just call the theorem above. So this theorem, we just call the theorem above. I just compute cx to ax, bx. And actually we evaluate C of 2. The running time of this, you can clearly see that this is O n log n. Complex. I should emphasize this is definitely complex arithmetic steps. So there are actually some further improvement along this. I mean, you can clearly see that the cost is O of n log n, but it's actually this number of complex arithmetic steps. So this is definitely something we want to be careful. And I think here, I mean, this is really something going into a very technical detail. So I'm not actually going to open the black box here. But the theory here is that actually by Schoenhage, and also Strassen, in 1971. And actually, we can show that integer multiplication integer multiplication x O of n log n log n beta operations. So instead of saying something a little bit weak, talking about like complex arithmetic steps, so the integer multiplication, I mean, in terms of beta operations, can work actually of O n log n times log n beta operations. So this is a theoretical perspective. So the next thing is about like a practice. So in practice, I mean, there are actually very good libraries that really optimize integer multiplication, because integer multiplication, as you can imagine, this is something just super important. I mean, in general, as long as you multiply something, you should begin with multiplying integers. So for instance, like the GNU multiple precision arithmetic library. This is also typically known as the GMP. I mean, uses like a brute force. I mean, just direct multiplication. We have been talking about the Karlsruhe algorithm, and also FFT, depending on the size of n. So I mean, in terms of like engineering perspective, because the GNU is a really important platform that optimizes, I mean, also including scientific computing such as integer multiplication. I mean, typically you can imagine that if you have like small numbers, I mean, for instance, like 3 times 7, I mean, you can just do this in the brute force sense. And if the number is super large, I mean, in general, I mean, in terms of a asymptotic bound, of course, n log n is going to be better than the Karlsruhe's n to the 1.585. So basically, if the n is super large, I think it is commonly people use FFT. And actually, if n is super small, I mean, it's just like a very small and just like brute force like multiplication works. Actually, for intermediate size, I mean, sometimes Karlsruhe also works well. So because Karlsruhe does not have this kind of complex numbers, and actually Karlsruhe is also relatively easy to understand. So this really, I mean, for even engineering-based packages, people also there are like people switch between the different method. I mean, the very brute force method, Karlsruhe and FFT, really depends on the size of n here. Okay, I guess this actually finishes the whole part of the divide and conquer. And I think basically for today, we also introduced integer multiplication, a matrix multiplication, and also this for almost 2 hours introduces fast Fourier transform convolution. I think it is very important. I mean, the technical details of the fast Fourier transform is a little bit evolved. I mean, you consider like the multiplication of complex numbers, etc. But nevertheless, I mean, here I think it's very important you remember this theorem that in general, I mean, even only with coefficient representation, multiplication of 2 polynomials only takes O n log n steps. This is called a convolution, and this is something that is going to be very helpful. And actually, have in our assignment, we are going to see a problem that uses convolution to solve some actually very important problems. Okay, so any questions for today's lecture? So I guess my original plan is probably starting from this lecture to talk a little bit on dynamic programming, but I guess today I'm probably not going to reach that since we only have about like 5 minutes. So maybe if you don't have any further questions, so maybe let's call it a day, and maybe let's for the next lecture talk about dynamic programming. So I think for last note, I mean, let me remind you again that basically assignment 2 is going to do next week, and keep in mind that you want to finish the assignments in time. And also in our, I think I also sent an email on this, but actually in our homepage, basically on our website, we also upload information for project proposal and actually a template on that. And if you have any questions about like the course project, also feel free to ask me. Okay, thanks for your attendance.